Hello, my name is Shashank Shekhar. So we have started the chapter solution. So we have completed two of the colligative property in the yesterday's class, which were basically the elevation in boiling point and the depression in freezing point. So we have seen how this number of solid particle, which on introduction can alter the colligative properties. So four of the colligative properties are to be studied, out of which two are already covered in the previous class. So which were, say, the first one was elevation of boiling point, in which we see that upon addition of solid particles which are non-volatile in nature, we see an increase in the temperature at which the liquid should boil, or the solvent should boil. So in this case, the solvent becomes the solution upon the addition of solute, right? So after the addition of solid particles, we see a elevated boiling point. Similarly, uh, we see a depression in this freezing point due to addition of the solid particle, and this elevation and depression wholly depends upon the number of particles, where it depends upon the amount we have added to the solution. So, and it does not depend on the nature of that solid particle. So we can take any non-volatile solid particle, and the elevation and depression will be same until and unless the amount that we have added was same. So this was the case that we have studied right now. So moving on to the next remaining two colligative properties, which are the osmotic pressure and, say, the relative lowering of vapor pressure. So the first one is relative lowering of vapor pressure, and the second one is osmotic pressure. So we'll see these two remaining colligative properties today. So if you remember, in the previous class, we have termed the formula for the change in, or the elevation in boiling point, as delta TB is equals to KBM, and delta TB is T final minus T initial. This KB is ebullioscopic constant, and it is for the solvent. So remember this thing more, you can say, accurately, because you may get confused. You are giving two solution and you are given 1 KB value. So you may search that, okay, we have given two solution, so we must have 2 KB value. For that case, you must remember that KB is dependent upon the totally dependent upon the solvent. So if you are given KB for two solution, and in both the solution the solvent is same, so will be the ebullioscopic constant, and I am writing it here also, that it is for the solvent. M is the molality of the solution. So you can see that there is a direct relation between the number of particles and the change in, or the elevation in, boiling point. Similarly, if we are looking at depression in freezing point, we have this delta TF is equals to KFM, where KF is the cryoscopic constant and delta TF is T initial minus T final. Why is it so? Because we are seeing a depression, means the final one is smaller than the initial one. Therefore, we will take T initial minus T final. Okay. So this is these are the two colligative properties, and these are their formulas. Now we will move to this relative lowering of vapor pressure. So what we will see initially. So what is this relative lowering of vapor pressure? We will see this, and we will see its formulation, that how it is formulated. Also, we will see that it is derived from Raoult's law, right? So for those who do not who are not aware about this Raoult's law, so I have made it clear in the previous class only, that you should once revise this Raoult's law to understand the relative lowering of vapor pressure. So for those who don't know, I want to make the statement that Raoult's law says that the partial pressure of any substance in a solution is directly proportional to their mole fraction. And the more general statement was, the partial pressure of volatile substance is directly proportional to the mole fraction of that substance in the solution. And then we remove this proportionality sign and introduce the proportionality constant as P01, where P01 is the vapor pressure of the pure form of that particle or that volatile substance. So this was the statement of the Raoult's law, and it is written as P1, where P1 is the partial pressure in the solution in the vapor phase due to first component P01. Sorry, this will be here. P1 is equals to P01, where P01 is for pure solvent or pure volatile compound, say. And this X1 will be your mole fraction in the solution of first component. So this was our Raoult's law. So we'll see that how we can derive the formula for relative lowering of vapor pressure from this Raoult's law. Then further, we will move to semi-permeable membrane. So it is basically a component of osmosis. So while we do osmosis, we use this semi-permeable membrane. So we'll first get to understand that what is this semi-permeable membrane. It is also often referred to as SPM. After getting the idea of this SPM, we will try to understand what is osmosis and what is osmotic pressure. Then we will move to reverse osmosis and the type of solution which is based upon the osmosis only. And at last, we will see some natural phenomena in the which occurs in nature, which represent osmosis or in which osmosis occurs. So these are our topics. So we will total cover 9 topics today. So the first and the foremost is the relative lowering of vapor pressure. So what is this relative lowering of vapor pressure and why does it happen? So I am saying from the start only, from the beginning only, that when we are studying this colligative property and the solute particles which we are adding are volatile or should be volatile, non-volatile in nature. Sorry, it should be non-volatile in nature. Now we have said that, okay, we have added a non-volatile thing. So Raoult's law said that the vapor pressure is only due to the mole fraction of the component that is volatile in nature. By which I mean that suppose we have a solution in which both of the solute and solvent are volatile. Then in that case, we will say that the partial pressure will be as the result of both the component. But if we have a solution in which one is suppose the solute is non-volatile and the solvent is volatile, then in that case the solute particles will have a negligible contribution toward the vapor pressure, while the most of the contribution will come from the solvent particles. So this is Raoult's law. So upon addition of this say non-volatile particle, so they cover the solution in some way. Okay, so they cover the solution in some way, and they do not allow the solvent particle to escape as easily they were escaping before or in the pure form. Due to this reason, we see a decrease in this vapor pressure, and this is called lowering of vapor pressure. This is called lowering of vapor pressure. So relative lowering, we will see what is the terminology mean, what is relative lowering. Through the formula, we will see it, right? And the equation governing the Raoult's law, I have mentioned it here also. It is for ith component, which says that Pi is equals to P naught I xi. So I have made it clear what is lowering of vapor pressure. Now we'll see the formulation. So if I put the formula directly towards you, so this is the formula. So first of all, you should understand what is relative lowering. So these terms represent the lowering. It is P1. Suppose P1 is the final pressure and P01 was the initial pressure. So if we take the difference between these two, that is P01 minus P1, then this is called lowering. It is clear from the term only. And if we divide it by the pure solvent vapor pressure, then it will be termed as relative lowering. Means we are considering the lowering of vapor pressure in relation with this pure component's vapor pressure. So we term it as relative lowering of vapor pressure or relative lowering in vapor pressure, right? Now what we are doing, we are representing this P01 minus P1. Sorry, this will be P01 minus P1 as delta P1. Delta represents the change, you know it very well. That is, delta is representing the change. So we put this fraction here, and we say that this is equals to the mole fraction of component 2, which is the non-volatile component here. So I should write here component 2 is non-volatile. Why I'm saying that it should be non-volatile? Because the lowering of vapor pressure is only the result of this addition of solid particle, which is non-volatile nature. So component 2 is non-volatile. So it is equals to the mole fraction of the component 2. So how we will write the mole fraction? So we will write it as number of moles of the second component by total number of moles, which is N1 plus N2. So this is our formula. For the case we take that N1 is much more greater than N2, means the solid particle is often present in greater amount than the solid particle. But suppose we take a case in which N1 is present in excess. Okay, N1 is present in excess. Then we can say that N1 plus N2 is approximately equals to N1. Why? Because the addition of this small amount to this N1 has not that much significant effect on this total product, on this total sum. So we can write it as N1 only. Now we again formulate this formula further. We remove this N2 term and we write it as N2 by N1. So our relative lowering vapor pressure in case of N1 much more greater than N2. In case of N1 much more greater than N2, we can write this formula as N2 by N1. So what is N2? N2 is number of moles of 2, which is solute, or you can specifically say non-volatile solute. Again, what is N1? It is number of moles of 1, and it is the volatile solvent. So you should remember each of these terms minutely, because you may get confused in exam that what is this N2 and N1. So you must remember this terms minutely. Now we know that the formula of number of moles is given mass by molecular mass, which will be W2 by M2, where M2 is the molar mass of 2 and W2 is the given weight of 2. Again, we can write N1 as W1 by M1. So you must know first of all that number of moles is equals to given mass by molar mass. So we are using this simple formula only, not a rocket science to understand this thing. So given mass we are representing by Wi, where I is for the ith component, by Mi. So we are writing the same thing here. Sorry, it will be represented by capital M. This will be small w. It is okay. Yeah. So this is the thing. So using this formula only, so for N1 we are writing that given weight by molecular weight of 1. So this was about the formulation of relative lowering of vapor pressure. Now you will see how can we derive this formula from Raoult's law. So let us understand this. So we know that from Raoult's law that the partial pressure of 1 in the solution is equals to the mole fraction times the partial pressure of 1 in the pure form. So we know this formula. Now what are we going to find here? We are going to find here the first the lowering of vapor pressure. So it will be delta P1. Okay, it will be delta P1. So we'll write it as P01 minus P1. We know the formula very well. It is quite clear to understand. Here P01 is for pure solvent and P1 is for solution. Solution is made up of what? Solute, which is non-volatile in nature, plus solvent, right? So these are our terms. So if you want to see the change in the vapor pressure, so initially we have only this, upon addition we have this. So it will be final minus initial. We can do the opposite also. We are eager to find the magnitude, or we are interested in finding the magnitude only. So we'll take the opposite sign, right? So it will be P naught 1 minus initial minus final, which is in a way change only. So do not get confused why it is not final minus initial. Since we are calculating the colligative property, and we have seen that always we have to find a value which is positive in nature. So if we till date we know the, sorry, if it is possible to find the magnitude without altering the sign, we will do so. So I put P naught 1 means P initial first and minus 5 final. So do not get confused with it. Now we can put the value of P1 from here, which says that from Rod's law that P1 is equals to x1 P naught 1 again. Now what we have done, we have put this P naught 1 1 minus x1 and taken this P naught 1 common, it will be 1 minus x1. This formula you should know. I have told you for the binary solution that, or for any solution we can say that chi I, where xi is mole fraction, is equals to 1. Summation of all the mole fraction of all the component is equals to 1. So if you have a binary solution, we will be having x1 plus x2 is equals to 1, and therefore x2 is equals to 1 minus x1. So I've used the same formula here. So I've replaced this 1 minus x1 by x2. So the formula we get at last will be delta P1 is equals to x2 by P naught 1, or we can write it as delta P1 by P naught 1 is equals to x2. So this is our relative lowering, and this is equals to x2. So in this way, we can get the relative lowering of vapor pressure from Rod's law. Now we'll move to osmosis, and we will try to understand what is this osmosis. So before moving to osmosis, let us get a clear idea of what is semi-permeable membrane, or SPM. So first, let us understand this. So if you try to just imagine a semi-permeable membrane, you can look at this thing. This section or this column, you can look at this column that is put between these two compartments. You can see a boundary here very clearly. Now, what is this semi-permeable membrane? If you want to imagine it, it is just a sheet that is containing a large number of pores which can allow only certain particles to pass through it. So it is, so you can say this is a very accurate definition for it. So what is the semi-permeable membrane? It is a type of sheet which is having porousness, or holes through which only certain size of particle can pass, or particles having certain size can pass, right? So I have written the same thing here. So what is the semi-permeable membrane? It is a continuous sheet of film that contain a network of sub-microscopic holes. So this is our network. First hole, second hole. I'm not telling about this inner thing. I'm telling about the gap. Okay, so you don't get confused that I'm telling about this small, you can say blue one. I am telling about the gap between these two black strips. So they are the sub-microscopic holes or pores. Now you know that the solvent particle, water or any solvent particle, are greater in size. So this is our solvent particle. Sorry. So solvent particle is smaller in size. So this is our solvent particle here, 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 here. All are the solvent particles. And this is our solute, which are having a greater size as compared to the solvent. Now what do? We put this membrane here. Now this membrane will selectively allow only to solvent particles to move here or there. I'm not talking about direction right now, that where it will move from here to here or to here to here. I'm just saying that this semi-permeable membrane will only allow the passage of the small solid particles through it. That's it. And rest of the remaining solid particle, since they are greater in size, so they cannot pass through. So they cannot pass through like this because of the greater size and the smaller cavity that is present between the pores. Okay. Now, if you say where does this semi-permeable membrane come from? So it can be from the animal also. So for inside our body, we also have a semi-permeable membrane. In plants also, they do have this semi-permeable membrane. Or pig's bladder, you can have this. Or parchment. Or it can be made synthetically from cellophane also. So these are some examples of your semi-permeable membrane. So you can take the semi-permeable membrane, and I will make sure that you get to understand this SPM because it will be used in your osmosis. Okay. So this is our SPM. So if, in a nutshell, if I want to say, so these are a continuous sheet of film that contain small subatomic pores that allow only the passage of small solvent particle rather than bigger solid particles. So they hinder the passage of this solid particle because of their greater size. Now, what is osmosis then? What is osmosis? So we know that the flow always takes from lower concentration to higher concentration. Keep this thing always in mind. So suppose we have two pressures, right? So and they are not two compartments in which the pressure is different. In one we are having say P1 and in other we are having this P2. Suppose P1 is greater than P2. Okay, P1 is greater than P2. Now if you connect this two, the flow will take from lower concentration to higher concentration. Okay, so the same thing is written here. So if we take two volumes, two liquid volumes, and we have different concentration in both this solvent molecule, means the solid is one solid is present in greater amount, and in the second solid is present in small amount. Now if we connect both this, then always the particles will flow from lower concentration to higher concentration. Okay, the particles will flow from lower concentration to higher concentration. Now what we do, we take such two such solutions. So in one which we have only solution, say we have only solution, and in other we have our solvent, and we put our SPM here. Okay, we put our SPM here. Now what will happen, we will see a flow from I think this one is written wrong. Okay, this one is written wrong. I'm getting confused also. So it will be from higher to lower, higher to lower concentration. Because if you keep a mind map of this, well, we have two compartments in which one is filled with high pressure and one is filled with low pressure. Then automatically the high pressure will try to get a release and will abruptly move to this lower concentration to maintain the equilibrium because of the pressure gradient. Likewise, we have this, say if we open the Coke bottle which is filled with high pressure CO2, so the CO2 try to escape is always tries to escape very you can say quickly out of the soda box so that the pressure can be maintained or the equilibrium can be attended. So similarly the concentration flow will be from higher to lower. Now what we are doing, it is, I think it is written right. So next we will see what is osmosis. Okay, so if I want to define osmosis in one place or one line, it is basically the movement of solvent particles from lower concentration to higher concentration. Now why does it happens? So suppose we have two solutions here. Say we have one of two liquids here. So one is solution only, and one is having solvent. Now we will say that it should have moved from solvent to solute, because from solution to solvent. So now we will move to osmosis. So what is osmosis? So osmosis, if I want to define it in one line, it is basically the movement of solvent particles from lower concentration to higher concentration. Where? From lower concentration to higher concentration. Why is it happening? To maintain the equilibrium. So suppose we have this two compartments which are attached through one tube and a semi-permeable membrane is placed in between. Now we will see the movement from solvent from solvent to the solution. So why does it happens? Suppose we have solvent particles here, solid particle in this case. They will be moving, they will be quite apart from here. And suppose we have solid particle in this solvent also, solution also. Now since this concentration is higher, it will be present in a dense amount. Now to maintain the equilibrium, the solvent particles will move from here to here. Okay. Now this will result in a smaller solvent particle than before, and hence in a higher concentration, because concentration, you know that it is something that is measuring the amount of solid particles in a given amount of solvent. So if we reduce the solvent amount by movement from this side to this side, then in that case we can increase the concentration of this compartment also, which can be made equal to this compartment. So due to this reason, the solvent particle moves from lower concentration to higher concentration. And for that case only we have put this SPM, because it may be possible that the solution on this movement can result in the movement of solid particles also. To prevent the solid particles from moving to here or here to here, we have put a SPM which allows only solid particles to move through, right? Now what will happen? So we have taken a case that's such that we have only solvent here in this compartment and we have solution. Now the solvent particles will start to move from here to here, because it is an area of lower concentration, or you can say zero concentration, and it is an area of higher concentration. So the water will move from here to here, and it will flow until the equilibrium is attained. And this process, this flow of solvent particles from lower concentration to higher concentration, is called osmosis. Okay, this is called osmosis. Now what will happen if we do not place the SPM here? If we do not place the SPM here, then what will happen? To maintain the concentration, the solution will flow from this side to this side, so that both of the concentration can be balanced. So if you want just to experience this, just take a small bottle filled with color. Okay, and now take water in the other way, and put that small bottle of color in that water. What we will see that color will expand quickly throughout this water to make the concentration equal. So if you put this color at a certain point, it will not try to remain at that point, because this will increase the concentration and disturb the equilibrium. So to make this evenly, this color will move throughout this, so it can attain the equilibrium in that way also. So if you do not put this SPM here, that case will only happen. So to do our thing more interestingly, we have put a semi-permeable membrane so that solid particle cannot move freely. So the other way is to move the solid particles to in the opposite side. So this is our osmosis. Next, we have a formula for osmotic pressure. So for that, you should understand what is this osmotic pressure. Now we have seen that, okay, we are having a movement of solvent particles from solvent to solution side. Now to keep this flow in control, what we have done, we have calculated a colligative property which depend upon the number of solid particle in the solution, and this this property is osmotic pressure. So if we apply that amount of pressure on the solution side, this will stop the flow of solvent solvent to the solution side. Means it will stop the flow from lower concentration to higher concentration, and we are representing this osmotic pressure by pi, and this pi is equals to CRT. What it is equals to? It is equals to CRT, where C is the concentration, R is the universal gas constant, and T is the temperature, and pi is the pressure we are applying on the higher concentration, so that the movement from lower concentration to higher concentration can be stopped. You get my point? What is osmotic pressure? It is the pressure we are applying on the higher concentration so that we can stop the flow of solvent particle to the solution, or from lower concentration to higher concentration, right? So if we move this formula more further, or if we evaluate this formula more further, so we'll put concentration as molarity. So till now we were using molarity. Now we'll use molarity. So it's basically N2 by V. So you have seen right now that we have taken three things: molarity, and mole fraction. Three of these things. So when we are dealing with gas, that is relative lowering of vapor pressure, we took mole fraction. When we are dealing with kind of a solute, or you can say solid, or you can so we were using in that case molarity. Now we are using this molarity. So it is N2 by V, where N2 is the number of moles of the non-volatile component, and it is divided by the volume V to get our molarity, multiplied by universal gas constant times T. Now what we will do? We will replace this N2 by given weight by molar weight, so that we can get a number of moles, and we are shifting this V on this side, or we are multiplying this V on this side. So it will be basically pi V is equals to W2 into R into T by M2, where M is the molar mass or a molar concentration, this M, okay. R is this universal gas constant. Sorry for this I, it is written wrong. Okay. Pi is the osmotic pressure, T is the temperature in Kelvin. This will be C here. Next, since we are interested in finding the molar mass, we will put this M2 here and put down this pi V here to get our molarity. Sorry, molar mass of the second component. So this is our osmotic pressure. Now we will see some more terminologies that are related to this osmotic pressure. The first one is reverse osmosis. So initially we were seeing that, okay, the solid particles were moving from this to this. So this was our normal case, in which the solvent particles were moving from lower concentration to higher concentration through a SPM or a semi-permeable membrane. Now I have said that pi is the pressure or the osmotic pressure that we apply to just stop the flow of this solvent particle from this to this. Okay, so this is our pi. Now what happens if we apply a pressure greater than this pi? Okay, so what we are doing here is that we are taking a piston. Okay, we are taking a piston and we are applying pressure here, and we are applying pressure in such a way that the pressure that is opposed on this, or that is imposed on this salt water, is greater than our osmotic pressure pi. So as this pressure is greater than pi, becomes greater than pi, then the flow will take place in the opposite direction. Means from higher concentration to lower concentration. Then second thing, it is possible that salt water will flow from here to there, but we know that we have put upon a SPM here, so it will only allow the solvent particles to move through these pores. So the water molecules start moving from this side to this side. Now what is the application of this? So you can see very clearly from the image only that we have put this salt water here and this fresh water here. Now we are applying pressure and we are getting water, which is fresh water. Okay, so what we are getting fresh water through the with the help of this reverse osmosis. Okay, so this is an application of the osmosis in which we get pure water from salt water by application of this pressure, which is greater than our osmotic pressure. So the same thing written here. So direction of osmosis can be reversed if we have a pressure that is larger than the osmotic pressure, and it is applied on the solution side. Now what will happen? The pure solvent will flow from the solution through the semi-permeable membrane, and this process is called reverse osmosis. What is this called? This is called as reverse osmosis. So this is our reverse osmosis. Now next we'll see some types of solution. So this all solutions are based upon our osmosis. The first one is isotonic. So as the term says out, it is iso, means same. So two solution which is having same osmotic pressure at a given temperature. Now this is to be mentioned. At a given temperature, we are talking about all these things at a given temperature. So if two solution are having same osmotic pressure at a given temperature, then these two solutions are called as isotonic solution. Now what will happen if we place these two solutions, suppose 1 and 2, in two different compartments, and in between these two we have put a SPM, that is semi-permeable membrane. So what will happen? There will be no net flow if the both solutions are isotonic, if the osmotic pressure is same. Okay, so this is our isotonic solution. Next is hypertonic solution. So what is hypertonic solution? So it is having a higher concentration of solute than the another solution, meaning water will flow into it. What will happen? Water will flow into it. So suppose we take the example of blood cell. So what happens? So if we take blood cell or any cell, we take a cell and put it in a saline solution or a salt solution. Now you will see that if the concentration of the salt solution is greater than a certain given amount, I think it is 0.9%. So if that solution, that salt solution is having concentration greater than 0.9%, then in that case, the the water will move through this semi-permeable membrane, and we will see that, okay, our cell is filled with water. So this is the case of you can say you have seen this thing also. If you put out your hand for a greater time in water, you will see that your hand swells. So it is basically due to the flow of water from outside towards your tissue. And since your tissue contains semi-permeable membrane, it only allows the flow of water from outside to inside, and your skin swelling takes place. So this is a case of hypertonic solution. Similarly, if we take something, some water which is having a lower concentration, and you put your cell or you expose your cell directly to that water which is having a concentration less than 0.9, which is the concentration of salt inside the cell, then you will see that all the water will flow from the cell towards the solution that is present outside. So the water will flow out of this cell, and you will see that the cell will shrink. Okay, so these are the two cases. So the first one is called the hypertonic, in which we take a solution that is greater than the say outside, and we see that all the water flows out. And in the opposite case, we have the hypotonic solution. Okay, so this was our hypertonic and hypotonic. So you should remember all these three terminologies: isotonic, hypertonic, and hypotonic, and you must remember the example along with it. So this was the type of solution that we are having. Next, we will look at some natural phenomena that occurs in front of our eyes. The first one is the water movement from soil into plant roots and subsequently into the upper portion of the plant. So it happens partially due to osmosis. So some capillary movement is also involved in this, but osmosis also has a role to play. So I have told you earlier that, okay, the concentration, the movement takes from lower concentration to higher concentration. So we have our soil contains the minerals. Okay, so it has a lower concentration because the water that is present inside the plant is having lots of minerals and say fats not waters and minerals. So what will happen? The water will start to move from lower concentration to higher concentration, that is upside the plant, right? So in this way, the water move from lower concentration to higher concentration. And one more thing, why there is higher concentration upward? You can go and look into this, but it is quite interesting thing. You must look this water movement. And also it happens due to capillary movement, which is basically the result of surface tension, excess surface tension, right? So the first phenomena is water movement from soil towards the plant and to the upper parts of the plant. The second is the raw mango. So you must have seen the pickles. So if you have seen those pickles, or specifically mango pickles, you have seen that the mango skin looks to be shrinked or to be shriveled. Why is it so? So what do we do while making pickle? We take the say mango and put it in brine solution. Brine solution means containing salt and water simply, and that concentration is higher than the concentration that is present inside the mango. Now what will happen? To maintain the equilibrium, the concentration equilibrium, the water will flow from say our mango towards the solution, right? And this will result in shrinking or shriveling of this raw mango. So this is our second phenomena that we see in our daily life. Again, we can see wilted flowers revive when placed in fresh water. This is also a good example. So what will happen? So if you take fresh water, right, and if you put a flower in it, now flower, inside flower we have different type of minerals and all these things are present, and the concentration is lower there. Now since you are putting it in water which is having a lower concentration, okay, so it is having a lower concentration, so the water will move from inside to the flower side. Now what will happen? This will result in a kind of uh, supplement to this say flower, and it will be revived again. And it is, I'm not saying that it will be completely revived, but to some sense the flower gets you can say alive by this addition of water. So often you have seen that people, when they decorate their house, they put this live flowers in water to keep them fresh for greater amount of time, because this kind of gives them a supply of supplement from of water from outside the water to inside the flower. Next example, I have discussed this one. So it is the case when we place the blood cells in saline water, the water flows from the cells towards this uh, water concentration, sorry, towards this saline concentration, and the concentration is greater than 0.9%. Yeah, this concentration is 0.9%. So if we put our cells in a brine solution which is having NaCl concentration greater than 0.9%, then the water will flow from inside the cell to outside the cell, and it will result in shrinking of the blood cell or collapsing of the blood cells. So what is this result in? This result in edema. So edema is a skin situation arising due to flow of water into the cell. So it is just opposite of the case. So we have seen, so it is a case of hypertonic. Sorry, hypertonic. This is a case of hypertonic, and this is the case of hypotonic. So you can be asked this about this edema. So why does edema happen? So you should remember this. This is an important point to remember for your say from your CBSE point of view also, and say from your NEET point of view also. So this edema term can be asked. So what is this case? So it is basically we are putting our blood cells in a solution which is having a concentration smaller than 0.9%. Then in that case the water will flow from outside the cell to inside the cell, and it will result in you can say a case that is called edema. So this was our today's class. So basically we have studied two type of colligative property. So if I just write the formulas for you, the first one was RLVP. So we will term this, often term it as RLVP also. So this abbreviation stands for relative lowering of vapor pressure. So it says that delta P1 is equal by P naught 1, delta P1 by P naught 1 is equals to X2, which is mole fraction of 2 by N2 by N1 plus N2, where N2 is our, the second component is our solute, and it is non-volatile in nature. non-volatile. And the first is solvent, and it is volatile in nature. Now further we have assumed that suppose our solvent is present in a very great amount, so it will be N1 greater than N2, which will result in N1 plus N2 is equals to N1. We will write this again as N2 by N1. Now again, number of moles of N2 can be written as given weight of 2 by molar mass of 2 multiplied by N1, or you can say divided by given weight of 1 by molar mass of 1. Now if you put this thing up, it will be W2 into M1 by M2 into W1. So if this case is true, then we will use this formula. Otherwise we will use this one. And the next colligative property was osmotic pressure. So osmotic pressure is the pressure that we apply so that we can stop the flow from lower concentration to higher concentration. It is equals to CRT, where C is the concentration and it is termed as molarity, where we use this as N2 by V into R into T. N2 is number of moles of 2 and it is non-volatile, right? It is non-volatile, and N2 is equals to W2 by M2. Wholly we can write it as W2 RT by M2V. Next we have seen isotonic, means two solution having same osmotic pressure. Then we have seen some natural phenomena following osmosis. So with this I want to end this lecture. So in the next lecture we will see what is Ventov factor and abnormal mass. So we will see that how in some cases we cannot use this formula directly. There's some kind of modification in it. So we'll see those things earlier. So for now you should remember all these four formulas, which are elevation in boiling point, depression in freezing point, relative lowering of vapor pressure, osmotic pressure. Now next class we will use all this formula to get a new one, which is a kind of modified of the previous version, right? So thank you for today's times. You can stop the lecture.